Welcome back, everybody. So you may have seen an announcement from one of our TAs that he moved his office hours, and then you may say, I didn't even know we had a TA with office hours because they were put up in a sneaky way. So I added a link in the announcements to point you to them, but this weekend I'm going to update the page so that it's much more prominent. But we do have a TA having office hours from 4 to 5 today, and check out the announcements on the Canvas page. Okay, so other things, so start sharing my screen. So I wanted to make two kind of notes about the problem, the long example we were doing last time with the E or F or G parts. One of them, and both of these are fixed in the notes that I posted with Module 2. For one, we were talking about this machine with good and defective parts, and we were talking about a bunch of probabilities like this, and it was really hard to keep track of everything. And so although random variables are supposed to be real numbers, I went back and typed it up this way. So defective and good. And now it's much more clear, I think, because there were these ones and zeros, and some of them were time steps and some of them were states. And the other thing is that I had a mistake in there that was not, the problem was I wasn't thinking about the problem we were in. I just was doing kind of a generic thing. And that is that last time I said, what is the probability that x48 is 0 given x47 is 1 and I don't know what I had, I think 30 is 9. And I said that this piece of information doesn't matter and that you just get the first two. But I forgot that we were in a problem where the space was 0 and 1. And so x30 can't possibly be 9. And so there's a real problem with this statement because it's not a probability 0 thing. This first probability here has, if you write out the conditional probability, it has that x30 equals 9 in a denominator. Right? So x48 is 0, x47 is 1, x30 is 9, and then the two guys after the line. And in the particular problem, and I forgot that I was in a particular problem, this can't happen. So we would have probability 0, which makes this whole thing undefined. So that's not good. And I think I also cleared that up in the post-it notes in Module 2. All right, so at the end last time, we started to see something that looked a little bit like matrix multiplication. And now we're going to see more of that. And we're going to talk about something known as the Chapman-Kolmogorov equations. So we have transition probabilities. This is a lowercase p sub ij, and this is the probability you move from state I to state j in n steps. And we are always assuming a time homogeneous Markov chain. So this would be the same thing as maybe starting at some time m and then going to some time m plus n. Doesn't matter. And then we put these into a matrix called the transition probability matrix. And I'm using this kind of double-lined P. And it's just a matrix, which could be an infinite matrix. But in the ith row and jth column, we've got the little Pij. I don't know, I'm just saying in that column, I'm not doing anything with the other entries or saying they're 0 or anything. Okay, so last time we looked at a two-step transition. It was like a probability that x2 is 1, given that x0 was 0. We skipped over the time step 1. And we worked it out by conditioning on the value of x1. And then we all noticed at the same time, it was an awesome moment, that what we were doing kind of looked like a matrix multiplication. And so I want to formalize that, and I'm going to formalize it with something known as the Chapman-Kolmogorov equations. But first, one more point of notation. So this is new. So a lowercase Pij, and then a superscript n in parentheses. Duret does not use parentheses here. In his book, it looks like an exponent, and this is not an nth power. But this is the n-step transition probability. So this is the probability oh man, and that's a mistake on top. That's what I wrote on the top line. I went from time 0 to time n. So rather than, I'm just going to fix the top line, this up here is the n-step transition probability. I had meant to just recap the one-step transition probability. So it should have gone from time 0 to time 1, but it didn't. So now let me fix it on the left side. So I guess I don't need to finish writing it down here, but let me write it in English. So the probability you go from state I to J in n steps. But definitely make sure you catch this correction up here because I did write n time steps in there. Okay, so we can put these n-step transition probabilities into an n-step transition probability matrix. So I am going to use the same kind of superscript and n in parentheses to denote the matrix filled with Pij n. So that's supposed to be representing the ijth entry. And that's the probability of moving from state I to state j in n steps in time. And this is not Pij to the nth power, which is why I don't like Duret's notation. Okay, so, and this is a pretty common notation too. Okay, so we are ready for what are known as the Chapman-Kolmogorov equations. This is going to be a result that we're going to use for several things, but one thing we're going to use it for is to prove what we think we saw last time about powers of the transition matrix. By the way, in the new notation I gave, the n-step transition probability, we can talk about moving in 0 steps. The probability of moving from I to j without moving in 0 units of time, it's like a Kronecker delta. It's 1 if j is already equal to I, because you can't go anywhere in 0 units of time. And it's 0 if j does not equal I. So we can kind of talk about 0-step transitions. But back to the Chapman-Kolmogorov equations. There's more than one way to write this down. There's more than 2 ways to write this down, but I'm going to pick 2. My favorite is this. So Pij, and then I always say super because I don't want to say to the like it's a power, super n plus m. I can write this as, so this is the probability you go from state I to state j in n plus m units of time. And what I'm going to do is kind of condition on where I was in the middle at some point, at the point m. So we're going to prove it. Let me just write it down. This is the sum over all k in the state space of the probability of going from I to k in the first m units, and then from k to j in the remaining n units of time. Totally not surprising, I think, given the independent transition things we sort of looked at last time. And so this is going to be for all. I'm going to start using more mathy notation. So if you haven't seen this upside down A, it means for all. Integers n greater than or equal to 0 and m greater than or equal to 0. And another common way that it is written is, this one is not as elegant. So the probability of going from I to j in n plus m units of time, we can, sorry, that's not what I want. I just want n there. Sorry about that. This is the sum over all k in s, the probability you go from I to k in some m units of time, and now m is going to be restricted to be less than n, and then you go from k to j in the remaining n minus m. So this is for all n greater than or equal to 0, and for m taking on the value 0, 1, 2, up through n. That one's a little clunky, if you ask me. Okay, so let's prove it. And then this is basically what you're seeing in here is like this sum and these guys, this guy looks like the elements all the way across the ith row of the transition matrix to the m. And this looks like all the elements down the jth column of the transition matrix, the n-step transition matrix. And we have matrix multiplication going on right here. So we'll conclude that at the end, but let's prove this. I'm just going to prove the first one. So proof, and I should write proof of first case, but I'm lazy. So little Pij super n plus m. This is equal to, you don't have to write any of this, but I definitely wouldn't be writing this first part, but I just want to stress it right now. And that is that it's a transition in any m plus n steps. So that's a little kind of L. This is the probability you go to state j in n plus m steps in time, given that you started in state I at time L, but because everything's time homogeneous, we can just start from 0. And in the future, I am just going to start from 0. So we've got time homogeneity. And so this is just the probability xn plus m equals j, given x0 is I. And so I'm just going to condition on where we are at time m, and let's do it. So condition on where we are at time m, and I can be many places, so we're going to sum over those. So this is going to be a sum over all k in the state space S of the probability that xn plus m equals j, given xm equals k and x0 equals I, times the probability xm equals k, given x0 equals I. And then we get to use the Markov property in that first probability to get rid of this guy. So MP for Markov property. Because once we're given the value of the chain at time m, we don't care about earlier time steps. And this is exactly what we wanted, because this is the sum over all k in the state space. The probability we go from k to j in n units of time. And then the other one is the probability we go from I to k in m units of time. And if you look back, that's exactly what we wanted. They're not in the right order, but we were trying to prove this. Okay, so we talked about powers of the matrix, and remember, we are, well, we don't have to remember anything. Let's look at what we have here in the circled Chapman-Kolmogorov equation. On this left side, I have the ijth entry of the n plus m step transition probability matrix. And then right in here, I've got everything as we run over k, I've got the ith row of the m step matrix. And then finally get those right order, yeah. And then finally the jth column of the n step matrix. So we're multiplying everything across the ith row component-wise with everything down the jth column and summing. That's matrix multiplication. That's proof right there that we have, so this implies that the n plus m transition probability matrix is the product of the two matrices, the m step 1 and the n step 1. And there's nothing special on, I chose to condition on where we were at time m. I could have chose to condition on where we were at time n and really interchange the role of m and n on the right-hand side of Chapman-Kolmogorov. So we also have this going the other way. So this product is commuting. We could get the n-step transition matrix times the m-step 1. And now bring it on home into powers of the original matrix. So i.e., like one example of this is well, first to note that this notation, this kind of bold P with this super 1, this is the transition matrix full of one-step probabilities. So this is just our original P. And so if we want to look at the transition matrix of probabilities in 2 steps by Chapman-Kolmogorov, we know we can break this up into a one-step matrix times a one-step matrix. And by the line just above, we know that this is the original matrix times the original matrix, which is now a matrix squared. So all the way on the left, this just specifies that I've got probabilities in there, which are the probabilities of moving from some I to some j in 2 steps. And then this is just, I've squared the matrix. And they're the same. And let me just write one more line. So like the probability matrix of moving places in 3 time steps, we can write as like the 2-step matrix times the 1-step matrix. And based on what we just wrote above, this is p squared times p, so p cubed. So yeah, you can just take powers of the matrix to find multiple time step transition probabilities. But keep in mind, so in general, we have the n-step transition probability matrix is the original one to the nth power, but we do not have the little lowercase pij, and this is not the little lowercase pij to the n. I mean, that's just not how matrix multiplication works. You don't square and cube the entries. It will work with more than 2. So up here, where I said condition on where we were at time m, we could actually put 2 variables in here and condition on where we are at 2 different time steps. And so we'll get something very similar here. So if this exponent was like an n plus m plus l, we would get an m1, an n1, an l1, and we'd have 2 sums because there'd be 2 of these intermediate places. We're trying to go from here to here, and after this amount of time, we could be anywhere, and after this amount of time, we could be anywhere, and then we're where we want to be. So absolutely, you can have more. All right, next up is going to just seem out of nowhere, but it's going to be a really useful kind of tool for us, and that is the idea of an absorbing state of a Markov chain. All right, so here's a definition, and that is an absorbing state and of a Markov chain, but that's really all we're talking about. So I'm just going to write absorbing state. And this is a state that once you hit it, you can't leave. You get absorbed. So once you reach or hit this state, you can't leave. And sometimes this happens really naturally. For example, the gambler's ruin problem. You know, you come to a craps table and you have some amount of money and you're going to leave when you hit $0, or I don't know, maybe you have some upper limit, but 0 is going to be an absorbing state because once you hit, well, no, because then you mortgage your home and you fall in with seedy loan sharks, and they follow you around for the rest of your life. But in theory, 0 should be an absorbing state because once you have 0 money, you can't play the game anymore. So that's a naturally occurring absorbing state. So just get that down here. That's the idea of a gambler's ruin. So you hit $0 and you are stuck, in theory. So an absorbing state could naturally occur, or we can induce an absorbing state to help us solve a problem. So sometimes you want to induce an absorbing state to help us solve something. Okay, so here is my example. I'll just write it here, and I don't want to scroll too fast if you're writing notes, but on any given day, Rufus, who you met last time, one of my dogs, he is either happy, H, or just okay, an O, or sad with an S. So Rufus is either happy, just kind of okay, or sad. And I'm going to assume that his moods follow a Markov chain and are governed by the following transition matrix. So assume Rufus's moods are governed by or follow a Markov chain with transition probability matrix that I'm going to give to you now. We're going to try to answer some questions, and we're going to use absorbing states, and we're going to introduce absorbing states into the problem, even though there isn't going to be one there. So he is happy or okay or sad, happy, okay, sad, with probabilities across the top. I'm going to put a 0.6, 0.3, and 0.1. These numbers are not actually important, but they might be if you're trying to trace like what came from where. And across the second row, I'm going to put 0.2, 0.5, and 0.3. And then across the last row, 0.2, 0.3, 0.5. And yes, he stays in the same mood all day and somehow magically turns over at midnight. So I set it up so that he kind of tends to stay in the same mood. You know, if he starts happy, then he has a high probability of being happy the next day. And if he starts okay, he has a high probability of whatever. They're made up numbers, and Rufus is always happy. So but he will kill you for a tissue. Okay, so here are my questions. I have a few. So the first one, question one, is Rufus is currently happy. Oops, that's really messy. I'm just trying not to have too much dead time while I'm writing, so I'm writing really fast. Currently happy. And I want to know the probability that he is not sad on any of the 3 following days. So what is the probability he is not sad on any of, this is not better. I'm filling up the time by saying my words very slowly as I'm writing them, on any of the 3 following days. So let's set up a Markov chain to write this, that's a question mark. Let's figure out what we want to solve, right? So I'm gonna let xn be his mood on the nth day. I don't like splitting my board like this. It destroys the illusion, but I feel like I'm scrolling up too fast for people who are writing. So what we want is he's currently, so we're gonna just label current time times 0, and then we'll care about what happens in time 1, 2, and 3. So what we want to know is the probability that sort of x1 is not sad, x2 is not sad, and x3 is not sad, given that x0 is that he's happy. And here I think you're going to see some of the sort of beauty of Markov chains, that they make otherwise tedious calculations much easier. Because the brute, let me get the matrix. The brute force way to do this would be just to sort of list out and sum up all of the probabilities. If I wanted to do this by brute force, I would kind of arrange the moods like this. I would say, okay, this is current, and he's always happy currently. And then I want to look at all the other things he could be, which could be happy, 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 okay, all the way on down to like, okay, okay, okay. This is not the way you want to go, but you know, if you have to, you have to. And so the probability for each of these are disjoint events, because he's currently happy, and him not being sad in any of the next 3 days means he either had happy, 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 or he had happy, happy, okay. He can't have them both happen at the same time. So these are disjoint events. So if I can find the probability of each one of these lines in my little table, I just need to add them up because everything's disjoint. And so the first one is he's always starting at happy, and we're going to happy. And so that's this 0.6. And then he's going to happy again. So that's another 0.6. And then finally happy again. You know what, I'm going to take the P off of this so it's not so wide. Okay, so there's one more 0.6 on there. And the next one, he goes from happy to happy, and that happens with probability 0.6. And then he goes from happy to happy again, and that's another 0.6. And then he goes from happy to okay, and that's over here. That's a 0.3. And on down the line, just to complete this, the last one is happy to okay, which is 0.3. And then okay to okay, which is 0.5. And then okay to, excuse me, okay, which is 0.5. And so if you add these guys up, you get, I think I did this. Yeah, you get 0.609. And that is the ugly brute force way to do this. And another ugly brute force way to do this would be to list out, to start with your happies over here, and then list out all possible combinations that have at least one S in them, and compute that total probability and do a 1 minus, because that's the complement of this event. So that would work as well. But I told you I didn't, but I am going to make you love absorbing states. So let's do it. So an alternative here is to make sadness an absorbing state. Okay, so make S an I'm going to define a new chain. I don't really think I need to define a new chain. Like I could call it Y sub n. I think I can get away without that notation, but it will have its own new transition matrix. I'm going to call it Q. And so we've got happy, okay, sad. And we're just going to make it the same as the P matrix, but we're going to make sadness an absorbing state, which means that our last row here is going to be 0, 0, 1. Once he's sad, he's always sad. And then I'll fill in the rest, 0.6, 0.3, 0.1, 0.2, 0.5, 0.3. check this out. I'm going to go up to my table again. Sorry about all the scrolling. The yellow table on the left-hand side. So these are all the probabilities we want to compute, and these are probabilities that run with the P matrix. Those are all the states we care about, like the transitions, happy to happy to happy to happy, happy to happy to happy to okay. And computing them with the P matrix, we get the 0.609. Now, if we run these two mood processes in tandem, like using the same random bits to choose probabilities, then they would run exactly the same way until the P matrix hits the sad state. So like if our chain with the P matrix went from happy to okay, our chain with the Q matrix would go from happy to okay. And the P matrix would keep evolving moods, but once he hits sadness, in the Q matrix, he gets stuck at sadness. And so for any path of the original chain that I'm calling the P chain that goes through S, that ever hits S, the other chain, the Q chain, will get stuck in S at that point. So you can imagine like happy, happy, okay, sad, happy, okay. Like that's the original chain, and the other chain sort of running in tandem would be happy, happy, okay, sad, and now forever sad. But up until that point, they have the same probabilities. So the answer is going to be, we don't want sadness in our P chain. So that means we don't want our Q chain to end in sadness after 3 steps. So the answer is the starting at happy to sad entry. The answer is 1 minus the happy to sad entry of Q to the 3rd power. Because in the Q matrix, if we are sad by the 3rd step, that could mean that we went, he just got sad the 3rd day, but it also could mean he got sad the 2nd day or the 1st day and was stuck there. So this is really quick. I'll give you we'll cube the matrix, and the answer here is 1 minus 0.391. I'll write that up in the notes, the actual cubed matrix, but it is 0.609, which is what we already got. So we created something absorbing to help us solve a problem. Yeah, so I got the question, why is it the 1 minus the happy to sad entry of Q cubed? Let me go back to just doing it with P. I did say it as a kind of just an extra statement, but I didn't emphasize anything. So we could do this whole list thing again with just P, and instead put all of the different outcomes that have at least one sad thing in them. And then we can total that, and then 1 minus that would be all the probabilities for all the outcomes that did not have sadness, which is what we want. So this is the this notation is going to be wrong, but this is going to be like the probability not sad. I'm not being very specific with the conditional stuff. Not sad over 3 days looks like this, and this is going to be 1 minus the probability sad at least 1 day. It's just really bad notation because I didn't write enough. At least one of the 3 days. And so I'm doing the complement thing down here, and I don't have to worry about looking at whether or not I'm sad. So let's say today is Monday, and then we have Tuesday, Wednesday, and Thursday. We don't want him to be sad on Tuesday, but we'll hear about it on Thursday if he got sad Tuesday, because the Q chain will keep him sad. So if we compute the probability of going from happy to sad in 3 days in the Q matrix, that takes into account all those different possibilities that he got sad on Monday, or he got sad on Tuesday, or he was sad on both days. And so I'm going from happy to sad in 3 steps. So that's why I cubed the matrix Q. And yet I don't want him to be sad. So it's a positive story. So I'm doing 1 minus that. It's the complement of him being sad. The actual question was, so his moods are governed by a Markov chain. I am watching the time. The moods are governed by a Markov chain, and he's currently happy, and we want the probability he's not sad on any of the 3 days. And so that's the actual question. And there's no M and N. The M and N came in the Chapman-Kolmogorov equations, which gave us the explanation about why you should take powers of the matrix, but we're not using that explicitly in this problem. And yeah, so if you cube the Q matrix, when you cube it, I didn't cube it, but I haven't written it out yet. Don't write this, it'll be horrible notes. But if this was like cubed, that's awful. Then you want to go from here to here in one step because it's already a 3-step chain. And yet we don't want to be sad. We want the probability he's not sad. So we did 1 minus. By the way, if you cube your Q matrix, then this answer should be the probability of going. I'm going to use a notation here that I don't really know how to denote this. So this could be Q cubed, and then we could take the happy to happy entry plus Q cubed, the happy to okay entry. That's what that notation is trying to say. So I don't want the subscripts to be in there before it's cubed. So this is me trying to say I've cubed the matrix and I've grabbed the happy entry and the happy okay. And I want either of those to happen. And the 3 of these guys, I'll cut and paste, not gonna be worth it. So the 3 of these guys, starting happy, he has to do one of these things after 3 steps. So these probabilities will add up to 1. Okay, so watching the time, I've got 4 minutes. I promised to give you those back, and I will. I'm keeping track, but let me do question 2, or at least get question 2 started. No, I'm really serious about that. I really don't want to take your extra time up. So this one we'll probably only get to start, but that is that Rufus is happy on Monday. I want us to be really clear here about what is today, what is yesterday. And I want to know, and I am taking the time to write the English out because part of the problem is translating this into what you want to solve. So what is the probability that, okay, so what is the probability that he is happy on Friday, given he was not sad all week? I don't know what all week means. Do we go back to Saturday or Sunday before the Monday? It doesn't matter. Once we fixed his mood on Monday, we don't care about the previous stuff. So what we're trying to do here is basically map the days. So the days are Monday, Tuesday, Wednesday, Thursday, and Friday. And I'm going to kind of map these to time steps 0, 1, 2, 3, 4. And then what we want is the last thing I'm going to do because I won't be able to finish it. We want the probability that on Friday he is happy, given on Monday he was happy, and also given that xi is not sad for I equals 1, 2, and 3. So I'm almost out of time. I'm not really, but I'll still be in the middle of this problem and I don't want to just cut off in the center. So see if you can figure this one out. We'll start with it next time and see if we get the same thing.